Hello calculus kids, this is Mr. Bean, and in today's lesson we're going to talk about summation notation with respect to Riemann sums and how you can take a whole bunch of Riemann sums, add them all up, and then basically get the area under the curves instead of just an approximation. So let me show you what I'm talking about here. You don't need to write any of this down yet, I just want to show it to you on here. Let's say we take a Riemann sum with only one subinterval. So if we had, if n equaled 1, in this case n equals 1, you'd have a rectangle that looks like this. And I made this a left Riemann sum, so you can see here on the left. So left Riemann sum, there's my rectangle. This would be an approximation of the area from -1 to 6, because that was what our interval there said, -1 to 6. Okay, so that's not a very good approximation. So how about we take two subintervals? If we had two subintervals, left Riemann sums, there's one rectangle, there's one, that's nice because this is now underneath, it accounts for some of this area, so that's probably a little bit better of an approximation, but again, not very accurate. How about we take three rectangles? So if we'd looked at that area, maybe a little bit better, about 4 rectangles. Ooh, getting better. Let's go up to 5 rectangles. And so you can see here, the more rectangles I have, a little bit better of an approximation it would be. If I keep going, now this one's weird. Why is there no rectangle here from 6? Because the height of it was 0 for the left. But if we keep going and just add more and more, you can see here, if we get lots and lots of rectangles, now that's starting to look like the area under the curve. You still have some gaps in here and some little overestimates, but it's pretty good. And I could keep going more and more rectangles and approach infinity. And once you get to infinity, well, you can't ever get to infinity, but once you get to really, really, really big, and you can use a limit, which is what we're doing with calculus, you can get the area under the curve. That's what we're going to do today. We're going to add up an infinite number of rectangles. Okay, so how can you do that? I'll get to this here in just a second. Let me show you first. If n is the number of subintervals on the interval, in other words, the rectangles, what is the width of each subinterval? So in other words, what would the width, how far apart are these? The way you calculate that, we did this in our last lesson, is you take b minus a, so how far is this interval, and then divide by the number of subintervals, or the number of rectangles you have. That's delta x. Delta x just means the change in x. So it's how wide a rectangle is. That's this right here, delta x. That's what we're talking about. Okay, what about if, think about this one other way, if we have the number of subintervals approach infinity, what's the width approaching? So the width, this delta x, if we have an infinite number of rectangles, it's getting smaller and smaller and smaller. So this width shrinks. I just held my hands in the air and you can't see what I'm doing. It's getting smaller and smaller and smaller and approaching 0. All right, so now let's do some summation notation. So the sum of all the areas of rectangles is this. So start writing this down, and as you're writing, I'm going to talk about each one of these. So this delta x1 times f of x1, this little x1 just means the first subinterval or the first rectangle. So our first rectangle, its width, times the height of the first rectangle. Okay, so that's what this is. This is like our area of rectangle number 1. And then we're going to add rectangle number 2. Again, this is area of rectangle number 2, all the way up until you get to the nth rectangle. So that's all of the rectangles, width times height, width, height, and so forth. So what if we wanted to say n is approaching infinity? That's where it's a little bit weird. If we say n approaches infinity instead of a very specific number, we come down here and we use summation notation. So some of you may have covered this in a pre-calculus class, and some of you, this might be the very first time you've ever seen this notation. It just depends on the teacher, on the school you're in. So this summation notation, it just means you're taking the sum of things that are coming up after this from 1 to n. So usually this is a number. We'd say like from 1 to 5. And so you're going to plug in a 1, plug in a 2, plug in a 3, plug in a 4, plug in a 5. Well, if n is infinity, or it's approaching infinity, that means the sum is going to just keep going and going until you get to a specific number. So let me show you what I have here. So you write this out, this weird thing here. So as you're writing, let me explain what each of these are. This here is the width. We've been talking about that. So that is the width of your rectangle. b minus a divided by how many rectangles you have. You're going to multiply that by a y value. See, this is f of something. Just like up here we had f of something. F of something is a y value. So this is your height of that rectangle. And width times height will give you the area of it. And then the sum means you're adding every single one of the rectangles up as n approaches infinity. So n, these n's here, are approaching an infinite number of rectangles. So you're adding up an infinite number of rectangles, but each rectangle is getting smaller, 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 smaller. So it's going to converge to a specific value for the area under the curve. So what is this going on here? You're going to take f of this big mess, a plus b minus a over n times k. What in the world is this? Let me show you a quick little example before we go on to some other examples. But so maybe on the left side of your notes, this might be a good place to write it. If I say the function f of x is equal to, I'm going to say 2x plus 1. And let's do on the interval from 3 to 5. So if I just say from 3 to 5's interval, let's come up with some summation notation for area under the curve that gives us the area under the curve for this weird problem here. So I'm going to write out what I have in blue. b minus a, so 5 minus 3 is 2 over the n. So that's this first piece, the width. And I'm going to multiply it by f of this. So here's my f of x. 2 times, now I do the x. X is going to be a plus, so this is 3 plus. 3 plus, and then I have b minus a over n times k. I already figured out what b minus a over n is, right? That's 2 over n. So 2 over n times k. And then I have the plus 1. Plus 1. So this looks really confusing, but it's not that bad if you can start to understand what's really going on here. This is the width again, 2 over n. And then I'm going to plug in, I want a y value for the k, the kth subinterval, the number k rectangle. So I'm going to start at 3, because that's where my interval starts, and I'm adding a width. So see this 2 over n? That's the width. How many times am I adding it? K number of times, depending on which rectangle I'm talking about. So I start at 3, and if I added just 1k, that'd be adding 1 width. So I'm from 3, I'm going over 1 width of a rectangle. If I was doing the second rectangle, I'd add this twice. Third rectangle, add this 3 times. And so then you just plug it into your x value here, and then you still have to do the 2 times the x value plus 1. That's what's going on. Okay, I know this looks a little bit confusing. If you kind of re-listen to that, hopefully that'll make more sense as you try and work through how you plug these things in. Now let's, oh wait, we have to do one more type of thing, and that is another way of writing summation notation is this. You could say, instead of n approaching infinity, you could say that delta x is approaching 0. Delta x, again, is the width of your rectangles. So if I had my rectangles, and this is my width right here, delta x, if that thing is approaching 0, getting closer and closer and closer to 0, that's the same thing if you're on a set interval of a to b. And that's actually the same thing as the summation notation from up above that we just did. Okay, this one's not used as often, but it does mean the same thing. All right, now to the whole point of our lesson. This is why we're doing this. We are trying to take this crazy, weird summation notation, and let's come up with a new way of writing this, because this is really convoluted. It's confusing. It's kind of messed up. It's hard to follow, right? For a lot of people, this is like, whoa, there is a nice, clean way of writing this in calculus, and that is something called the definite integral. Here's the definite integral. We'd have this weird little symbol that looks like an S, almost like an S, and you have a lower limit of A and an upper limit of B. That just means we're doing the interval from A to B. If you take the integral from A to B of f of x, that is the area under the curve. That's what this symbol means. And the way you do it is you do this weird, crazy summation notation stuff. Now here's the good news. Later on in this unit, we will have some fast ways of being able to calculate this. We do not have to do it like this with the summation notation. So the point of this lesson is I want to make sure you can convert in between these two types of notations. That this is the area under the curve, adding up all of the rectangles, which is equivalent to just saying this. Okay, so let me show you what I mean. So if we have this definite integral here from 2 to 6, can we write this in summation notation? Well, sure. Here, let's just take this answer up here. We're going to write the limit as n approaches infinity of, and then you got to do this weird summation notation, which I'm awful at. And then I'm going to say from k equals 1. Now this k, that variable could be anything. Sometimes you might see I. It doesn't matter. Usually I see a k. So k equals 1 up to n, which is, again, the number of rectangles we're going to have, and that's going to approach infinity. And then I have to multiply it by, all right, here we go, b minus a over n. So it's 6 and 2, that's a difference of 4. So it's 4 over n. So 4 is my interval divided by the number of rectangles I have, times it by f of this. What is that? So it's the function is right here, x squared minus 3. So I'm going to do a bracket here, and then I'm going to have x squared. So this whole thing gets plugged in, this right here gets plugged into the x. So my a, let me just write this down. My a for this problem is a 2. My b for this problem is a 6. So I'm going to say 2 plus, and then the b minus a over n, I already figured out, it's right there. So 4 over n, and then times the k, close the parenthesis, and then I square it. So that whole thing is my x, and then subtract 3, bracket, and then that's it. I've got it all covered. Okay, this is the summation notation for that integral. We would be taking the width and the height of every single rectangle as the rectangles approach infinity, the number of rectangles. Okay, that's the point of this lesson, being able to recognize summation notation and then backwards going the other way as well, which is what we'll do for this problem, and this is going to look weird. So I'm going to show you that there are 3 possible ways of writing this. Though I think the easiest way to do this is if I just show you 1, 2, and 3. There's actually probably a lot more than just 3 ways, but these are 3 definite integrals that all would work for this problem. So some of you might be thinking, oh, go ahead and write this down as I'm talking. Some of you might be thinking, what the heck, Mr. Bean, how am I supposed to know which integral it applies to? Well, that's where this would be a multiple choice problem, right? Okay, it would be a multiple choice and they'd say, okay, which one of these or which one of these 3, maybe 2 of them, maybe all 3, which ones work? Okay, so, and I'm gonna show you how you would check this. So first, let's identify this 6 over n. So if you don't have them written down yet, go ahead and write them down, pause the video and write them down. I'm gonna keep talking here. So this 6 over n represents, remember that's your b minus a over n. So I know that b minus a is 6, and that tells me that these have to be 6 apart. So this goes from 0 to 6. And then I have 4 plus 6n over k. Well, why not have this 4 here? Isn't that kind of like your a plus, right, from before what we worked on, the notes up above? Well, it could be, which is when we get to part B, you'll see that. But it could also be nothing. Like it could just, your a could be a 0. So if you look at this, it would work out. You'd have 0 to 6 for the 6 over n. And then here you'd say 4 plus, and then your x is 0 plus 6n k, right? That is your x right there. For if we follow the a plus, b minus a over n. Okay, so that's why this one works. Here's another example. If we started at 4, that would include this 4 as your a, and it still has a difference of 6. So that's why this one can work. You'd have this x right there would be your 4 plus 10 minus 4 over n k. And that's where it would work out to be the same thing. Now, probably the one that's even more confusing, that's a little bit more challenging for you to come up on your own, would be that this one also works. And so what I'll do is, let me just write this out. So this is the same thing as saying, I've got the 6 over n in this case, but this is only 0 to 1. So I'm going to say 1 over n, that's the width, and I'm going to times it by this thing. 6 times 4 plus 6, and now I have to plug in what is my x. My x is a plus b minus a over n k. Oops, Okay, all right, that is my x for this part. So a is a 0, 0 plus. And then b minus a over n, that's just 1 over n, because it's only going from 0 to 1. So 1 over n, k. And then that whole thing, oh, that was like a bracket. That whole thing is being squared. See this 4 plus 6x quantity squared. 4 plus 6x, and then that whole thing is being squared. All right, now if I simplify this, this becomes 6 over n times, and then I have 4 plus 0 is gone, so it's like 6 times 1, 6 over n, k, quantity squared, and then it matches up with this. Perfect. Okay, so sometimes what you might have to do is take the integral, the definite integral, and convert it to summation notation to check and see if you did it right. Okay, that's the more challenging one right there. So I'm going to make it easier, because what I'm going to do is I will tell you what the lower limit should be, and you don't have to create them hard like this. You'll be able to check the answers and just and be able to check in between. It's going to be one of these or one of these. I will make this easier for you. Unless it's a multiple choice problem, then you have to check through each possible option. Okay, so here's a good example. We're going to take this series that we have going on here. We're going to be adding everything up and figure out a definite integral for it. So to start off, let's set up my integral, and I'm giving you that the lower limit a, this lower limit is going to be a 0. So I have to start with that. Now my delta x, or my change in x, is b minus a over n. So each interval is delta x. That is equal to 2 over n. So if this is equal to 2, then that means my limits have to be 2 apart. So if the bottom one's a 0, that's a 2. All right, next. The other thing we think about is, let me write this here, a plus, and then we have our delta x, the b minus a over n, times k. So this is what gets plugged in to f, right? F of this thing. This gets plugged into the x. When you see this plus 3, a lot of times people immediately think that plus 3 is the a, which it could be. We could write one that where the a is a 3, but I told you that a had to be a 0. So that changes it. We can't just go from 3 to 5 and then be done with it. What we're doing instead, let me show you this. We're going to write 1 over, and then what goes in here is this is the thing that's changing each time. That and that and that, all the way until we get to 2 over n. So now how much is it changing by? It's 2 over n, 4 over n, 6 over n. It's changing by our delta x, this. So this is our b minus a over n times k. So the first one is going to be 2 over n. The second one will be 4 over n. The third one is 6 over n. So this right here is just my x plus 3. I could put that in parentheses and then say with respect to x. So this does take a lot of practice, and I will tell you on the AP exam, the nice thing is that they will always have this be multiple choice, so you'll be able to pick out of your multiple choice answers which one fits to this one. But the a was a 0 in this case, so I knew I didn't have to have any extra numbers in this, and that this term that I've circled in each one of these was just that part there, the b minus a n over n times the k. Okay, let's do one more problem. So what are we going to come up with here? We want an expression for this sequence of numbers. How are we adding this up? So this is like a series. What is this definite integral? It's an approximation. Oh yeah, that's the key here. This is an approximation for what definite integral? Okay, so here's what the answer is, and let me explain it. 0 to 1 of cosine x. And that's it. So how in the world is this a possible approximation of this thing? Well, the 1/10, if I took this 1/10 and distributed it to every single one of these, it's like I would have this 1/10 times cosine of 1/10 plus 1/10 times cosine of 2/10. And so forth. I could just keep going, distribute, all the way up until I got cosine of 10/10. So this is your width. This is your height. All the way up until you get, so plus dot, 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 plus 1/10 cosine of 10 over 10. So what we have going on here is that every one of these has a width of 1/10. What that means is that this 10 is actually not part of the integral. See, the 10 represents how many rectangles there are. That's your n. Your n equals 10 in this case. So what I have here for my answer for this problem, it's a little bit long. You don't have to write this whole thing down. You just want to write something that helps you understand this. So what I said here is 10 represents how many subintervals there are, or in other words, how many rectangles we have. And it has nothing to do with the function. I could have said 50 instead of 10 and to make it more accurate, but my answer would still be the same. So if every single 10 was a 50, I would have to go up to 50 subintervals. So it would be 50 over 50, but the answer would still be exactly the same here for the integral. Okay, so this is what we're practicing to try to recognize. How are these series and sequences, when we take the summation of them, how do they represent a definite integral? Because this is the area under the curve of the cosine graph from 0 to 1. Okay, I know this was pretty confusing. When we get to an AP exam, you're likely only to see maybe just one problem on the AP exam that's on this, but it's still a healthy thing to know how to convert between the two of them, because the integrals are the basis of the whole second half of calculus this year that we'll be doing. All right, so rock that mastery check, and I'll see you back in the next lesson.